So section 4.9, I should say, is going to talk about antiderivatives. Now let me kind of remind you a little bit where we've come from and where we're going, because we're getting closer to the end game here. So that end game is going to involve stuff that I told you about at the start of class. Now at the start of class, we worked with limits and things like that. And limits eventually led to the derivative. The derivative was this mythical point where the slope of the tangent line, or slope of the secant line, became closer and closer to the slope of the tangent line. So why is this not working? Yeah, all right, I guess it's this way. So we started out, we took 2 points that were on the equation of a graph, and we let them get closer and closer and closer together. We took the limit, and that became the derivative. So that was a big part of our work in the first part of the course, but now we're getting closer towards the end game in this course, and what we're going to finish up with is trying to find the area underneath this curve and above the x-axis. So this part right here. The first step of this is to undo what we did earlier. The first part of what we did earlier was we had derivatives. Now we're going to want to try and find the antiderivative. What did you differentiate to get something like we got? So for instance, on your most recent test, one of the problems that you had when you differentiated it, you got this thing right here. You got y equals x squared minus 6x plus 8. So literally when I wrote the test, I started out with this, x squared minus 6x plus 8, and that's a really awful looking 6 there. 6. And why did I start with that? Well, because it factors pretty easily, right? I mean, I think if you're at this level that you should have no problem with this. X minus 4, x minus 2 equals 0. It worked out pretty easily. But this is really the derivative of some function. And what we want to do is we want to go backwards. We want to ask ourselves, well, what did I differentiate to get this? That is, if you were writing this test, what should you put in there as f of x? Assuming that, like me, you wanted to be nice to your students and give something that worked out pretty easily. You didn't have to use a quadratic formula. So is that a good goal? Should we be nice to each other? Yes. Okay, all right. So we'll do that. Now, to do this, let's first of all figure out, let's take a look at what happens when I have a polynomial, say p of x equals x to the n. I'm just going to differentiate that one term. P prime of x, well, let's see. The n comes down, and then what else? Subtract 1. If I'm going to go the other direction, if I'm going to say, all right, well, what did I start out with? Call it maybe capital P of x. Then I got to do these two operations in kind of the opposite order. So for that, you're going to start by adding 1 to this exponent, x to the n plus 1, and then divide by that same exponent. So that's the antiderivative of terms like that. So you're doing two things. Start by adding 1 to the exponent and divide by that same exponent. So let's see if we can apply that to this term right here. So if f prime of x was x squared minus 6x plus 8, well, let's see. Then f of x, so it's antiderivative, you're going to start by adding 1 to the exponent here. That's going to give me a 3. And then divide by that exponent. Okay. Now what happens when we differentiate a constant? Do we really pay much attention to constants? Yeah, we just kind of leave it there. So let's just leave that 6 there and pay attention to the x. Now I don't really have an exponent written here, but what exponent is understood to be here? A 1. Good. So we got a 1 here. If you add 1 to the exponent, you get a 2. And then you want to divide by that same exponent, which is another 2. Let me ask you to think a little bit. What would you start out with? What would you differentiate to end up with an 8? 8x. Yeah. Now, if you really wanted to, you could think of this as 8 times x to the 0 power. That's fine, but this is just going to be an 8x. And that's not bad, except we're going to be a little bit more general than that. What happens when you differentiate a constant? Yeah, you get a 0. So we're just, to be the most general we can be, we're going to call it 8x plus c. Now when I wrote your test, I just chose a number for c. I didn't just give you a generic number, I just picked a number for c. There is a little bit of cleanup we can do. 2 goes into 6 3 times, so I'll rewrite that as 1/3 x to the 3rd minus 3x squared plus 8x plus c. There you go. So a nice problem so that when you differentiate it, you've given your students something that they can easily work with and factor, rather than some ugly quadratic equation or which you're going to use a quadratic formula to find its roots. So, yay. So that's where we're headed with this kind of stuff. Let's try a few more. Let's work with the examples on our handout. We can start with a nice friendly one in example A here. So here's your function, find the antiderivative. A lot of times if we have an f of x here, I don't have the prime, then the antiderivative I'll denote with capital F. So if you're starting out with just an f of x and you want to find its antiderivative, then we generally use a capital F to denote that antiderivative. Now once you get the antiderivative, then simplify it. Now, kind of like our previous one, it's not really written, but it's understood that there's a 1 here. So your first step is going to be to do x to the 2nd divided by 2, and here a 7x. And finally, don't forget that constant. It's kind of funny, but at this point moving forward in your math career, constants are going to get really abused. I mean, you're just going to be really kind of sloppy and loose with constants. And, you know, for me, there's a little bit of pleasure in that. But overall, we are going to get pretty loosey-goosey with our constants. So we end up with 3x squared plus 7x plus c. Nice.
Is the antiderivatives and integration are same?
And yeah, there's a very close relationship between antiderivatives and integration. Yes, yeah. So this would be sometimes called the indefinite integral of this function. Yeah. But when we get to definite integral, we're going to introduce a little bit more of an idea to the notion of integration. Let's keep going. Capital F, in this case, I am going to ask that you simplify these things if you don't mind. So start by always adding 1 to the exponent. So that's going to be a 6 here, and then a 6 underneath here, a 5 here, and a 5 here, 3 and 3. And please don't forget that constant. Even though we abuse them and toss them around and don't treat them very nice, we still need that constant there, and it's worth a point. You know, just bottom line, it is worth a point. Now you should simplify that. Overall, we'll get f of x is x to the 6 minus 8/5 x to the 5th minus 3 x to the 3rd plus your constant. So that's what I'll be looking for as a final answer. Are we okay with those? All right. Let's try one that gets a little bit tricky because we have these fractional exponents. Now, just because we have fractional exponents doesn't mean that our work changes when we're working with these antiderivatives. So, let's see. Do I have enough room here? I think I'll move on to a different sheet of paper just for this one. So let's do f of x. This is example C. F of x is 12x to the 5/7 plus 5x to the negative 6/7. We want to find the antiderivative, so f of x is 12x to the 5/7 plus 1 divided by something, and then 5x to the negative 6/7 again plus that 1. And we're going to divide by that same exponent. Now it's up to you. I guess it depends on how good you are with the mental math. What's 5/7 plus 1? Yeah. 12/7. Yeah. So you're going to take this and divide by that 12/7. And then negative 6/7 plus, call it 7/7, right, is going to be 1/7. So I'll divide by 1/7 here. I'm forgetting something. What am I forgetting? What am I going to lose a point for? Plus C. Don't forget that constant. Now, if you're looking at this going, oh man, fractions is not my jam, that's okay. I'd rather see you get it right than anything else, so just take an extra second. Take 12 divided by parentheses 12/7, and bam, you get 7. So you get some nice simplification there. So we end up with 7x to the 12/7 plus, when you divide 5 by 1/7, that's like multiplying by the reciprocal. That's going to be 35x to the 1/7 plus a constant. Looks pretty good. What if I wanted to check it? Arm. If I'm looking at that going, you know, that looks good, but I'm nervous. How would you check it?
Just find the derivative.
Yeah, just find the derivative. So if you differentiate this, you get 12/7 times 7. Well, the 7s will cancel and leave you with a 12. Subtracting 1 from that is going to give you 5/7. So we're looking good there. 1/7 times 35, likewise, is going to give you the 5. Subtracting 1 from 6, or subtracting 1 from 1/7 is going to leave you with negative 6/7. Derivative of constant is 0, so that one's looking pretty good. Nice. Well done, Arm. Let's keep going. Let's see. Let me just go back here. I'll let you work on example D for just a moment. What would you do with example D?
Raise it to a power?
Could. could. I mean, you could always write that as 3 to the 1/2 if you wanted to. Somebody said just a constant.
Yeah, where's x?
There is no x, right? So if you really wanted to rewrite it, I guess the most useful way to rewrite it is square root of 3 times x to the 0. And as far as the antiderivative is concerned, then f of x would be square root of 3 x to the first power divided by 1 plus your constant. Or basically just the square root of 3 times x plus c. But the point of this one is that all you really had was just a constant. All right. And when you differentiate this function, the constant's going to go away. Derivative of x is 1, so you're just going to be left with square root of 3. So it wasn't meant to be really hard. Here's one that you're going to have to start thinking in a reverse direction. What do you start out with that you differentiate to get y equals a sine? What's derivative gives you the sine? So call it capital F of x. What should I write here? So look, the way I always work these things is I just test it. Derivative of cosine would be negative sine. Well, that's opposite of what I want. So I'll put a negative here. Derivative of negative cosine is going to be positive sine. That works. Let's not forget our constant, and yay, we're done. Nice. Nice. Why don't we try another one kind of like that? Let's do, say, g prime of x is cosine of x. What's g of x? Yeah, g of x would be sine of x plus c. It's annoying that there's not symmetry between these things, that the derivative of sine is cosine, but the derivative of cosine is not sine. It's negative sine. So unfortunately, you don't have that symmetry. It's just a quirk of the way things work out. But, yay. Let's move on to example F. How are we looking there? Okay. Unfortunately, you can't find the antiderivative of the numerator divided by the antiderivative of the denominator. That's not going to work. What we'll do instead is I'll rewrite this as 4 over the square root of t. In fact, I'm not going to write it as the square root of t. I'm going to write it as t to the what power? 1/2 plus t over t to the 1/2 plus t squared over t to the 1/2. What should I do next? Terms, Maish?
I have a question. Like, could you just do the thing we were talking about before? Like, let's say the quotient rule do it by just like rewriting the t to the 1/2 as a negative t to the 1/2.
Well, say out right here. I'm going to write this as 4t to the negative 1/2. But how about the middle term? What should I write there? Is there anything I can write here? Is there anything I can do here? Yeah, the exponents subtract. When you're dividing things with the same base, you subtract their exponents. So maybe this is what you're suggesting, Mage, which is great. We'll subtract exponents here. I'll subtract exponents here, and I'll end up with t to the 3/2. So that's a lot more manageable than what we started out with. And I'll write this as capital G of t. Now here we got to be a little bit careful. If you add 1 to the exponent, what will you get? 4t to the what power? 1/2 divided by 1/2. Add 1 to the exponent here. Gabrielle, what would I get for the exponent then, please? If you add 1 to 1.5 or to 1/2, you get 1.5. So t to the 3/2 power. I'm kind of running out of room there. Let's see. Let me. I guess I'll just do it on the sheet here. So g of t. This is example F. G of t be 4t to the 1/2 divided by 1/2 plus t to the 3/2 divided by 3/2 plus t to the 5/2 divided by 5/2 plus our constant. I would greatly appreciate you cleaning this up a little bit. I'll do likewise, starting with this awful 2 here. But when you divide by 1/2, it's like multiplying by what? Multiplying by 2. Basically multiplying by the reciprocal here, so that will give me 8t to the 1/2. Dividing by 3/2 is like multiplying by 2/3. So 2/3 x to the 3/2 plus 2/5 x to the 5/2 plus a constant. Nice. Nice. Let's flip it over. Are we okay with this one? Let's see. Jameson, how would I check it if I needed to? If I looked at that and said, you know, I'm not so sure about that, it doesn't feel quite right, what could I do?
Take the derivative.
Yeah, take the derivative. And what should happen if I take the derivative?
It should turn back into the original form.
Yeah, it'll turn back into this, which if you get common denominators will eventually turn back to this. So, yeah, spot on. Thank you, sir. All right. Let's flip things over to example G. And one of the problems that you're going to see here is something that we haven't really touched on too much. There's so many rules for differentiation, so many different formulas you can remember and are asked to remember. I'm not going to ask you to remember all of them. I've tried to be select, even though it might not feel that way. So let's see, we've got f of x is 1 over x minus 1 over x squared plus 1 minus x squared. So in terms of the antiderivative, was it x to the 4th? My bad, thank you. X to the 4th. So in terms of the antiderivative, let me help you out with this middle term. What you differentiate to get this is the tangent inverse of x. But what I'm counting on you for is these other two terms. What do you differentiate that gives you 1 over x? Laura?
Isn't it the natural log of x?
Yeah, nice. Natural log of x. And James, how about, what do I differentiate to get x to the 4th?
X to the 5th?
Keep going.
Over 4? Over 5.
Over 5. Nice. And what else do I need here to finish up? Plus that constant. Yes. Need that constant in there. Nice. And wow, that's it.
That was easy.
Yeah. Nice. Nice. Lucas, something about that not looking too right?
I just know the middle one.
It's from teaching this. it's not a rule that we've gone over. I did prove to you the derivative of the inverse cosine and sine. We did derive that at one point. It's not something that we've really discussed. It's not a problem that I'm going to put on an exam for you guys, but there are a lot of these different rules that you can be aware of. Let me pull this one over. It's something I was searching for just a little bit ago. Yeah, right here. So there's a lot of different identities that when you differentiate the arc sine, you get this guy down here. Arc secant and arc cosecant, I've never used these. But arc tan, yeah, you'll see that from time to time, and arc cosine. So there are a couple more differentiation rules that you could use. It's just that you're getting enough in this course as it is. So I don't want to overwhelm you with some of these rules for differentiation. But yeah, you can actually prove that using implicit differentiation. It's where we get those things. In fact, let's take kind of a look back here at those rules for just a second as we look at example H. So example H. All right, so I hope you got a good look. Example H. We've got G of V is 4 cosine of V minus 3 over the square root of 1 minus V squared. Now, as far as differentiating or finding the antiderivative of this is concerned, one thing you could do for yourself is write that as minus 3 times 1 over the square root of 1 minus V squared. That might make this part a little bit easier to recognize. So it's going to kind of depend on you. But let's take kind of a look back here. Does anyone see a rule? Oh, come on, it's supposed to be bigger. There you go. Take a look at what we had there. We had a 1 over 1 minus V squared. Does it look like something that might match that here? Yeah, arc sine or arc cosine, depending on how you wanted to work it with that negative that's in the problem. But this much here, that's your arc sine. So I'll just go with that. So we can do capital G of V is going to be, well, let's see. We got to work backwards. What do you differentiate to get a cosine? Sine. Do I need a negative there or no? No, I don't need a negative. Minus 3 times the arc sine of V plus your constant. Nice, nice. Let's try example I. R of theta equals secant theta tangent theta minus 4e to the theta. Ooh. See if you can't find capital R of theta. What do I differentiate to get that? Ready, fire, aim. Okay. So, tough one to start out with. Holly, what do I differentiate to get a secant tangent? Yeah, just the secant. So it's a secant of theta minus what? Arm? Or Rahana? Yeah, 4e to the theta. Good. Plus c. Thank you so much for that. Plus c. Yay. Nice. Now, just to let you know, you're not always going to just abuse that constant. That it actually does get used. We're going to solve a few more problems that are going to start taking advantage of this constant and figuring out what that constant is. But are we okay with this one? Example I? There? Okay. Let's take a look at example J. F of x is 5x to the fourth minus 2x to the fifth. And they give us something peculiar. F of 0 equals 8. So that's interesting. They're sticking that in there with this. Now, the first part of this should be pretty simple, so I'll give you a few seconds to work on that. Find the antiderivative, capital F. And if you looked on D2L, there's actually a link that you can follow to all this stuff. All right, so if we add 1 to the exponent, we end up with an x to the 5th power here divided by 5. I'll do likewise over here. We're going to add 1 to the exponent, 2x to the 6th power divided by 6. And then the one other thing that I definitely need is that plus a constant. And it's particularly useful in this problem. Now, I do hope that you take the time to simplify that. That's x to the 5th minus 1/3 x to the 6th, because the 2 and the 6 cancel, plus our constant. Now, that constant can be anything. So let's try and understand the implications of that. Let's see. So, depending on the values that you choose for your constant, you can get a lot of different curves here. So let me change this to a C real quick. And then I can move this up and down. It can be anything I want. But I want to choose the particular value that makes the function go through this point, through 0 and 8. So that's telling me that, all right, I have to figure out what that constant is. And the clue that they gave you is that when x equals 0, y equals 8. So let's plug in that and see if we can't figure out what's going on. So I get 8 is my f of 0, which is going to be 0 to the 5th minus 1/3 of 0 to the 6th plus c. So basically that's telling me 8 equals c. 8 is the correct choice of c, so that my function actually passes through this point. This is sometimes called an initial condition, or in other cases it might be called a boundary value problem. In any case, my final answer is f of x equals x to the 5th minus 1/3 x to the 6th plus 8. So there's your initial condition and where you would use it. A lot of times, depending on the applications, This might be like a starting temperature or an initial velocity, whatever the case may be, initial height. But a lot of times you do have these initial starting problems, or initial starting values, I should say. Okay. Let me do example L, and then I'll have you do example K. So, yeah, I am kind of skipping up a problem. That's because I don't expect you to know the antiderivative of this one, although I do think we've mentioned it. So this is example L, and we've got f prime of, well, on the paper it says t, but I'm going to write x is 8 over 1 plus x squared, and f of 1 equals 0. Okay. It might help you a little bit to rewrite this as 8 times 1 over 1 plus x squared. In terms of finding the antiderivative, this is one of those ones that I don't expect you to know. And if you're kind of curious about, well, gee, how many different rules are there? Let me give you an abbreviated look at the number of rules here. Let's see, do I have, yeah, rules for differentiation. There's a lot of rules for differentiation, a lot of them. And I've tried to be nice to you guys by not giving you too many of them, but you can see that there's a lot here. And this is not an exhaustive list. There's a lot more. But in any case, the one we're interested in right now is this one right here. The derivative of the inverse tangent is 1 over 1 plus x squared. So it looks like we started out with 8 times something that differentiated that, and that would be the inverse tangent plus your constant. Just a little notation here. Instead of inverse tangent, tan to the negative first power there, what else could I write? Does anyone remember? What's another way to write? Yeah, arctan. This is just like square root of x and x to the 1/2. I mean, they mean exactly the same thing. They have the same derivatives. That's fine. Let's see if we can't figure out the rest of this then. F of 0, or excuse me, f of 1 would equal 0. So f of 1, let's see. Yeah, I guess I'll write it. Let me write it in red. F of 1 equals 0. F of 1 is going to be 8 times tangent inverse of 1 plus a constant equals 0. The inverse tangent of 1. Does anyone remember what angle has a tangent of 1? If you don't, if you're looking at that going, one thing that I need to remind you of is that your answer needs to be in radians. Answer in radians. Now your calculator is not going to be of direct help for you here, because if you do inverse tangent of 1, I don't think many of us are going to recognize what that is. Inverse tangent of 1 is going to be like 0.7 something, 0.785. Does anyone recognize that? Is that helpful? No. So briefly, and I mean briefly, you can put your calculator in degree mode, because it'll probably make more sense and jog your memory if you put it in degree mode. If I put it in degree mode, oh yeah. But that's not the answer that you put on your sheet. What is 45 degrees in terms of radians?
Is that pi over 4?
Yeah, this is pi over 4. You can go back and check it. You can do this. You can do pi divided by 4 and go, oh yeah, now I remember. So, and another thing you could do here, you could take this answer and divide it by pi and see the answer that way and say, oh yeah, 0.25, so that's 0.25 pi. But one way or another, you've got to realize that this is 8 times pi over 4 plus a constant of 0, pi over 4. Those cancel, they give me 2 pi plus c equals 0, so c equals negative 2 pi. Nice. Your final answer for the antiderivative then would be capital F of x is 8 inverse tangent of x minus 2 pi. So that's what I'd be looking for as a final answer there. Nice. Comments on that one? Are we all right there? Keegan, looking good? All right, cool. All right, now I promised you the chance to try one of these yourself. So why don't you work with example K? If you're doing this at home later, then you can pause the video and then fast forward it to find out the answer. What's one thing you might do to help yourself out with at the start here? How else might you rewrite this? Yeah, you might want to start by rewriting that as x to the 1/2. And help each other out. Kata and I will walk around.
That's cute. I just thought of it. I did.
So
That is cool.
when you plug in 4, your antiderivative equals 22. So you want to do
Later on in
20
the
plus
class,
C
we'll go
equals
helpful.
22. And then you can find C.
Three things. You change the pad. Let's do. When you simplify this, you should remember 2x over 3x. 3x equals 2, right?
Yep.
And if you're
I
on
know I started helping out
if you take the 3 divided by 3 over 2, that should be 2. That should get 2 up. Because you have 3 divided by 3 times. Mm-hmm.
And then I just like.
Well, you don't forget your plus C.
Mhm.
Plus C. So it's this. Actually, it's not 4 squared. It's just. No, no, this should be a 1 to start with. All right, so the antiderivative is next. Yeah, okay. It should be 2. It should be 2x to the 3 halves. Differentiate it with x, you give it 1. Differentiate 2x to the 3 halves. So 2x to yeah, because you add 1. Here's what's going on.
I can just like do it over.
Well,
I kind of just did a lot in my.
this should just be f prime of x still, because you're just rewriting it. But you accidentally took the antiderivative at the same time.
Oh, so
This should be a 1 here, plus 3x to the 1 half, and then you find the antiderivative. Okay. So you did the antiderivative twice here, but you really meant to rewrite it, so that should be a 1. I'm afraid that's right.
Screw me like that.
yeah. But still, that was something before.
Yeah. There's nothing like that for antiderivative.
Oh, you can. You have to set it up that way. Like the way we're doing it.
That's the only one I know how to do it. Yeah. All right, so let's look through here. First things first, we rewrite the function as 1 plus 3x to the 1 half. When you find the antiderivative of 1 is just x. For this part, add 1 to the exponent, divide by that same exponent. So 1 plus 1 half gives me 3 halves. Divide by 3 halves. There's my constant of integration. 3 divided by 3 halves gives me a 2. When you invert and multiply, the 3's cancel, leaves you with a 2. So there's your antiderivative. That's a couple points. All right, but get a couple more for finishing it up correctly by finding the exact value of c. You do that by using the initial condition, which was that f of 4 was equal to 22. So 22 equals the function evaluated at 4, which means we get 4 plus 2 times 8 plus a constant, which gives me 20 between these two, plus c equals 22, or c equals 2. Plugging that back into our function, we get something like this. Yay. Looking good there. Let me see if I've got a little decimals thing here to kind of finish that off. So problem K. So here's kind of a family of curves, lots of different ones, but you want the one that passes directly through the point 8 and 22. Where is that point? Yeah, right here. And so the correct constant to choose was when that constant was actually equal to 2. So this one right there. So nice, nice. Any other thoughts or comments on example K here? All right.
Do we need to be familiar with arctan for the exam?
So there's probably only 1 or 2 of these that I would ask you to be familiar with for the exam in terms of the inverse trigonometric ones. Let's go with arcsine and arctan. Even then, I'm not terribly gung-ho about using either of those, but I'll just limit it to those 2. So, but keep in mind, you do have the rest of your trigonometric functions here, and all these functions that have a derivative can be reworked in backwards form to find an antiderivative. So, we had the antiderivative of 1 over x was log of x. You can do the antiderivative of minus cosecant, cotangent, etc. So all of your rules for differentiation now give you an additional set of rules that you use backwards. So
Put that on YouTube.
yes,
Not our hands.
yeah. I'll put it in the handouts. It'll just be rules for differentiation. In fact, I've already got the PDF lined up for that. So thank you. Anything else? All right, let's put this one away.